Welcome back to the Deep Dive, where we take your stack of sources and deliver the essential distilled insights you need.
Today we are tackling it's maybe the single biggest limitation facing modern AI. And it's a very human one.
Memory.
Memory. It really is the final frontier for these large language models.
Yeah, think about the LLM you use every day.
Hmm.
Its knowledge of the world is, well, it's frozen. It's locked in from the moment training stopped.
Exactly. It's completely static. It can't learn from what you told it yesterday or even an hour ago. That knowledge is fixed.
Right. So it knows everything up to, say, mid-2023, but nothing after. And if you want a true assistant, one that remembers every single interaction from the day you started using it, let's call that its birth.
The current architecture just can't do it.
It just hits a wall. The context length wall. The memory required for that is, well, impossibly large right now.
And that's really what this deep dive is all about.
Yeah.
We're asking this core question. How do we build machines that truly remember, from their own birth right up to this very second?
Something that works like human long-term memory.
Yes. In a technical sense, it's about solving the problem of efficient, ultra-long context modeling.
And the payoff here isn't just, better chat histories. This changes everything about how we build AI.
It really does. If transformers could handle, let's say, a virtually infinite context efficiently.
Then you wouldn't need to cram all the world's knowledge into the model's parameters during pre-training.
You just retrieve it from the context in real time. That shift from compressing knowledge to retrieving it would just dramatically improve online learning.
But there's a huge hurdle, a massive one.
Two, really. The standard transformer is just bad at length generalization. It doesn't scale well to text longer than it was trained on. And critically, there's the computational complexity.
Ah, the curse of the quadratic. For listeners who haven't dealt with this math, what does quadratic complexity actually mean in practice?
It's simple, but it's devastating. If you double your context length, say from 4,000 tokens to 8,000,
The computation doesn't double.
it explodes. It goes up by a factor of 4. Then you go from 8,000 to 16,000, and it explodes again.
You can see why 16 million tokens is just a non-starter with standard attention.
Impossible. You need a fundamental architectural shift to escape that explosion, and that shift is what we're unpacking with this HSA ultra-long research.
Okay, so let's get into it. To get this ultra-long context, this 16 million token memory, the researchers say any successful model has to have 3 essential properties.
Right, these are the 3 pillars, and they stand in really sharp contrast to the old transformer limits. First up, you absolutely must have sparsity.
Sparsity.
Full attention over an infinite history is just.
Yeah.
It's not feasible. The system has to work like a human brain. You don't read every single memory you've ever had to answer a question.
No, you just pull the relevant bits.
You selectively activate and retrieve only what you need.
I like that analogy. So instead of the AI reading the entire internet library for every question, it quickly scans the card catalog and pulls the 3 relevant books.
Precisely. And that brings us right to the second pillar. Random access flexibility.
Okay.
Sparsity is useless if the model is just guessing which fragments to retrieve. You need a smart retrieval mechanism that's built into the model itself.
And it has to be optimized, I assume?
End to end. It's optimized under what we call the autoregressive loss, which is really just the model's ability to get the next word right.
So the memory lookup system is judged on how much it helped the final answer. That makes sense. What's the third pillar?
Length generalization. This is where almost every early attempt failed. You can't pre-train on 16 million token contexts. It's impossible.
Of course.
So the model has to be trained on shorter contexts, maybe 32,000 tokens, but then it must be able to generalize that retrieval skill to far, far longer ones, like 16 million.
And that really highlights why older methods just didn't work, like recurrent models, Mamba, for instance.
Right. They try to solve this by compressing all the past information into one fixed state vector.
Which sounds efficient, but...
It creates an information bottleneck you can't escape. It completely sacrifices that random access to specific distant memories. If a detail from 10,000 tokens ago didn't get squeezed into that one vector, it's just gone.
Gone forever. And sliding window attention has a similar issue, right?
Right.
It only looks at the most recent stuff by design.
By design. And even the older sparse attention methods, they struggled with this generalization problem.
Why was that?
Because the way they picked chunks of memory wasn't really learnable. It wasn't integrated. They'd use heuristics or rules to pick chunks, but If the selection system isn't being optimized for the final prediction,
It's not going to be very good at it.
it leads to inaccurate retrieval, and performance just tanks when you try to extrapolate to longer sequences. It never
Huh.
really learns how to remember efficiently.
Okay, this is where it gets really interesting. The core solution here is called hierarchical sparse attention, or HSA.
Yes. This is the mechanism that finally lets the system learn chunk selection and attention together end to end. It satisfies all three of those requirements we talked about.
And the best way to get your head around HSA is what? An analogy.
Yeah, the best way is to compare it to an architecture a lot of you might already know, mixture of experts or MOE.
Ah, the MOE concept.
Yeah.
So you have a giant model, but for any given input, a router just picks a couple of smaller, specialized experts to do the work.
That's the perfect way to think about it. So in MOE, a router picks the top K experts. In HSA, a learnable retrieval system picks the top K relevant chunks of past context.
Chunks of memory.
Right. And these aren't just raw text, they're summarized by something they call landmark representations.
So the landmark representations are like the index cards in our library analogy.
Yeah.
Little optimized summaries of each giant memory chunk.
Exactly. A new token comes in, it compares itself to those little landmarks, and it finds the top K best matches. But then the process is a little different from MOE. HSA performs attention chunk by chunk.
Wait, so it's not one giant, messy attention calculation.
No, it's several smaller, manageable attention calculations run in parallel, targeting only those few relevant pieces of memory.
That's very clever. But then how do you stitch the results, the actual memories, back together?
That is the key innovation. It's the fusion step. The outputs from each chunk's attention are weighted by their retrieval scores.
The scores that decided how relevant they were in the first place?
Precisely.
Yeah.
And then they're all summed up. So the system is basically saying, okay, this memory chunk was 70% relevant, this one was 30%, so I'll combine their outputs using those weights.
And because those weights are used in the final calculation, the retrieval system itself gets feedback.
It gets direct gradient updates. If retrieving a certain chunk helps predict the next word better, the system that retrieved it gets reinforced. The model is essentially paying its retrieval mechanism based on performance.
That's a huge insight. You bake retrieval right into the core attention mechanism. Okay, before we get to the full model, they also had this hybrid approach for positional encoding, right? Because positions over 16 million tokens must be a nightmare.
Oh, absolutely. Standard positional encodings just don't extrapolate well. So they used a hybrid strategy. For the short-range stuff, inside the sliding window, they stuck with ropey rotary position embedding.
Because it's stable and it works for local contexts.
Right. But for the super long range, in the HSA module, they did something counterintuitive.
What's that?
They used no PE, no positional encoding,
Not at all.
none. They found that for long-range retrieval, stripping out the positional data actually helped with extrapolation. Knowing what the information was more important than knowing exactly where it was.
Wow. Okay, so let's look at the full model. HSA Ultralong. This thing is an 8 billion parameter MOE model trained on, what was it, 8 trillion tokens.
A truly massive data set. And the architecture is this clever blend of sliding window attention, or SWA, for the local stuff,
The here and now?
and HSA for the global ultra long-term memory, and they share the KV cache from an intermediate layer across all the HSA modules, which is key to making it possible to even hold millions of tokens in memory during inference.
Now, this brings us to what I thought was the most complex part, the training. They found that if you just try to train this thing from scratch with a big SWA window, like 4,000 tokens,
Full thing fails.
the HSA module, the memory part, it just doesn't learn to generalize. Why on earth would that happen?
It's a core finding, and it's all about what they call developmental incentive. If your SWA is too big and capable, say 4,000 tokens, it can handle most short-range dependencies on its own.
So it never needs to ask the long-term memory for help.
Exactly. The HSA modules don't get meaningful gradients, they don't get that feedback loop we talked about, so they never learn the retrieval skill they need for true long-range generalization. The long-term memory gets lazy because the short-term memory is too good.
That is the AI equivalent of a helicopter parent.
Mm-hmm.
You have to introduce challenges to force the learning, so they had to kind of warp time during training.
That's a great way to put it. They developed this counterintuitive multi-stage training process. They started with a warm-up stage. They deliberately used a short SWA, only 512 tokens. This creates a huge memory gap, and they combine that with a global HSA, where TopKit was large enough to see the whole 16,000 token sequence.
And then they force-fed it memory tasks.
Crucially, yes. They randomly inserted synthetic tasks like needle in a haystack into 1% of the training data.
Forcing it to look beyond that tiny 512 token window to find the answer.
Exactly. You're training the HSA module to find that tiny piece of information hidden far away. Once that ability was learned, they moved to the pre-training stage.
And here they change things up again.
They increased the SWA back up to 4K tokens, but they decreased the HSA top K. They transitioned the model from that dense global retrieval back to the sparse attention mode they wanted,
And the final stage.
the long context mid-training phase. They switched to training data with much longer sequences, over 32,000 tokens, and raised the HSA top K again to cover that new expanded context.
So the big takeaway here is that the context length in your training data really, really matters for extrapolation. You can't cheat it.
You have to train on long contexts to generalize to even longer ones.
So after all that, the big question, does it work? Does it actually remember things from 16 million tokens away?
It does. That's the central finding. HSA Ultralong successfully extrapolates its retrieval ability from that 32K pre-training window all the way up to 16 million tokens. And it's not just theoretical, it holds over 90% accuracy on most of these in-context retrieval tasks.
And that's the boundary where basically every other model just crumbled.
And this one holds strong.
That is a staggering leap.
But
Did they have to sacrifice general performance?
yeah.
On standard benchmarks?
Not at all, which
Yeah.
is just as impressive. The 8 billion parameter MOE variant was on par with, or even better than, standard transformer MOE models. And after supervised fine-tuning, the HSA model actually pulled ahead.
Really?
Yeah, it scored about 1.3 points higher on average than a competitor model, even though it used fewer training operations. And they saw big gains in complex reasoning tasks, like math and coding.
But I want to go back to the most critical and I think most surprising insight for me, which is this persistent seesaw effect.
Ah, yes.
You're telling me that giving the AI less short-term memory during that warm-up stage made its long-term memory better. Why is that interaction so tricky?
It's exactly that developmental incentive problem. The research clearly showed that the smaller 512 token SWA led to better long-range HSA extrapolation than the larger 4K one.
Because the 4K window was just too helpful.
It was too good. It handled all the short-range stuff so easily that it basically starved the HSA module of the incentive it needed to learn that difficult underlying retrieval mechanism.
It's like taking the training wheels off the retrieval system early. You force it to work harder and learn how to find things far away. If the answer is always right next to you, you never learn how to make a long-distance call to your memory banks.
That is a perfect analogy, and this is a key tension they point out for future work. They also made another interesting point about scaling.
Right.
While the big 8B model and a smaller 0.5B model were pretty similar on pure retrieval, just finding the needle, the 8B MOE was consistently better at a variable tracking task.
A task that needs both memory and reasoning.
Right. It shows that more parameters really help for complex tasks that need joint reasoning and retrieval, not just passive recall.
So to sum up, HSA Ultralong is a really promising new paradigm.
Yeah.
It breaks that quadratic curse by doing attention chunk by chunk and cleverly fusing the results.
It's a very elegant solution, but, the paper is very clear that there are still some big open challenges.
Like the seesaw problem.
The HSAS way seesaw problem is a fundamental one. How do you use a long SWA, which you need for good short-range performance, without kneecapping the HSA's long-range ability, especially after fine-tuning?
And there's still an efficiency issue, right?
Yes. For shorter sequences, HSA is actually less efficient than super optimized kernels like Flash Attention 3, so they need more kernel-level work to make it the default choice for everything, short and long.
And there was one more constraint. Something about the attention heads.
That's right. It requires this limiting 16:1 ratio of query heads to key value heads. That creates a really severe information bottleneck on the key value side, and they need to figure out how to alleviate that.
So this research gives us a clear path to 16 million tokens of memory, which is incredible, but we're not at infinity yet. The goal is still an infinite long context.
Still the goal.
And if the training data's context length is so critical for extrapolation, it leaves us with this huge final question. What would truly infinite training data even look like? And how close can we get to human-like memory where a machine is just continuously learning and updating its own understanding without having to constantly retrain the entire thing from scratch?
That's the challenge, I think, that's going to define the next decade of AI development.
A lot to think about. Thanks for joining us for this deep dive.
My pleasure.
I'll see you next time.